So predicate logic consists of two kinds of statements, either universally quantified or existentially quantified for all xpx, or there exists xpx. There is no restriction on how complicated px can get. So these can be compound propositions. In fact, they can themselves be predicates. We will come to this later. These are called nested quantifiers. For now, we will focus on the case when the px is a compound proposition. How do you determine the truth value when px is a compound proposition? To determine truth value is we test truth values for all x in the domain. And this is the foundation. We're doing logic, so this is in a way, this is how it's defined. But this is not practical. For example, if your domain was all real numbers, then you're not going to try to build truth tables for every single real number, because there are infinitely many of them and you can even list them. So we'll see how to do this using truth tables for small domains, when the domain is like 3 things or 4 things. But when the domains get large, you have to use more complicated mathematics. So for small domains, you can use truth tables. For larger domains, you have to do more complicated math. And this video is about some way of doing this for small domains. So let's do an example. Let's have a domain that is only 3 things. Let's say the numbers 1, 2, and 3. And I'll consider the predicate for all x in this domain. X plus 1 is equal to 2x, or, brackets carefully, or x is even. So this is my predicate, and I need to figure out when is this true. I need to figure out if this is true, because I have a for x. So make that clear. To check if for x is true, need to be true for x equals 1, 2, and 3. And I'll do the same thing, but with existential afterward. Now you can actually just plug things in and check out by hand, but the book suggests that you use tables. So let's try using tables. The way we'll do this is we will vary x over all the possible things in the domain, and then find the truth values of each of the components. So the components here are x plus 1 is equal to 2x, and x is even. And then finally, I'll call this p, I'll call this q, and then the last one is p or q. So when x is 1, 1 plus 1 is equal to 2, this is a true statement. 1 is even, this is a false statement. Notice now our statements are depending on the variable. When x is 2, this is a 2 plus 1 is equal to 4, that is false. But 2 is even, that is true. For 3, 3 plus 1 is equal to 6, that is false. And 3 is even is also false. And combining these, the first one becomes true, second one becomes true because we are doing an OR, and the third one becomes false. Now, to prove for all, we needed it to be true for all x, and this is not true here. Not true. Or I'll write the whole thing again. For all x, x plus 1 is equal to x, and x is even, is false. Because we have a counter example given by 3. Now, if I were to do the same problem, but now using existential quantifier, or for existential quantifier, let's copy this. So let's change this to there exists. And now I want this to be true for some x. Now I don't even care what happens for later ones, x equals 3, even x equals 2. I don't care about this, because if you look at the first row here, then we have hit true. And that is all we needed. We needed it to be true for some x. And so I can say that for all x, oh sorry, there exists x. Or x is even. It's true. And it's witnessed by x equals to 1. That's it. So you can have compound propositions inside your predicates. And then you would test it by doing case-by-case analysis. Let's revisit a problem. Let's revisit something that we had seen in an earlier video. And this was, let the domain be all natural numbers. I don't need all. So let the domain be natural numbers. And now let me create this predicate for all x in this domain. X is even implies x squared is even. And let's find the truth value of this using this process. I start by varying the variables, but now my variable is natural, all natural numbers. So I have to build a truth table which is infinitely long. Then the first one is x is even. The second one is x squared is even. Let me call the first one p, second one q, and then the whole predicate is p implies q. So when x is 0, 0 is even, so that's true, and 0 squared is even, so that's also true. And true implies true is true. When x is 1, x is not even, so I don't even care what happens there. I'll just put this as true. Actually, let me just, for the sake of completion, I'll put it like this. For 2, it's true, true, true. Then for 3, you get false, false, but true, and so on. And so if I could build the whole truth table, I could conclude from this that for all x, x is even implies x squared is even is true. But of course, you can't go on for infinitely long time. That's humanly not possible. So we don't do it using truth tables in actual mathematics. We will prove this using mathematical induction. And mathematical induction is something we'll see in the second half of the course. So the rigorous way to prove most statements about natural numbers is not by building truth tables because of the infinite size of natural numbers, using this very strict technique of mathematical induction. That's it. So you can combine various propositions, make a big compound proposition, and use that as your predicate inside a quantified statement.